Okay, so the next topic is group homomorphism. In this, we've been given two groups, G comma star and H delta, and a mapping G from G to H. So for this mapping G to be a group homomorphism, we have to prove these three to be true. So the first one is G of A star B is equal to G of A delta G of B for all A B belonging to G. The second is G of identity element of G is equal to identity element of H. E of G obviously belongs to G and E of H belongs to H. The third property is G of A inverse. So A inverse is the inverse from group G, and so G of A is calculated and then the inverse is taken from group H. So G of A inverse belongs to H and A inverse belongs to G. So this might not make a lot of sense, but if you look at this example, it might become clearer. So we have a group R comma plus. So R is the group of real numbers with plus operation, and R naught is group of real numbers without the number 0 with the multiplication operation. So we've been given a function f from R to R naught such that fx is equals to 2 raised to the power x. So in the first one, okay, so the star is the equivalent of plus, and the delta is the equivalent of star, which is multiplication in this case. So g of a plus b, which is g of a star b, is equals to 2, and x is replaced by a plus b over here. So 2 of a 2 raised to power a plus b. So as we know that powers in plus can be written as multiplication, so that becomes 2 raised to power a into 2 raised to power b. Now g of a will be 2 raised to the power a instead of x, and g of b will be 2 raised to the power b. So we get 2 raised to the power a into 2 raised to the power b, which is the same as LHS. Therefore, the first property is proven. Now g of eg as we know is 0 because 0 is the identity element of plus operation, and eh is 1. So we get g of 0 is equal to 2 raised to the power 0, which is 1, and e of h is 1, therefore LHS is equal to RHS, hence proved. Third property is g of a inverse. Now we know that the inverse of plus operation is minus a, so we get g of minus a over here, which is 2 raised to the power minus a, which becomes 1 upon 2a. Now in this we have to calculate g of a, so we simply substitute the value of a in this and we get 2 raised to the power a. Now we have to find out the inverse of that with respect to the multiplication operation. Now it's just luck that in a multiplication operations inverse is raised to power minus 1, but this does not mean raised to power minus 1. It means that we have to find the inverse of the element inside with respect to the multiplication operation, which is in this case. So we get 2 raised to power minus a, which is equals to 1 by 2a, which is the same as LHS. Therefore, all three properties have been proven, and this is a group homomorphism. Now we move on to semi-group homomorphism. It's the same as a group homomorphism, except we take S comma star and T comma delta, which are two semi-groups, and the function f from S to T is a semi-group homomorphism if it satisfies this property. The rest two properties, these two properties, do not have to be satisfied in this case. Therefore, if this is proven, then it's a semi-group homomorphism. Now we move on to monoid homomorphism. Now for a monoid homomorphism, we take two monoid groups, S comma star with identity element ES and T comma delta with identity element ET. So for the mapping G from S to T to be a monoid homomorphism, this condition has to be true along with the second condition of group homomorphism. If these two are true, then it's a monoid homomorphism. Now we have kernel of a homomorphism. Now, so basically the only property that a kernel has to fulfill is that G of A, for any A belonging to G, the mapping of that element A should give the identity element of H. I'll explain with the example. So in this we have a mapping from F, and C naught is all the complex numbers whose with excluding complex numbers which have zero magnitude, and R naught are all the real numbers without the number zero. So both of them have the multiplication operation on them, and f of z is defined as mod of z for all z belonging to C naught. So if we see f of z1 z naught gives us mod of z1 z naught, and we know that if two values are multiplied inside the mod, we can write them separately also. So therefore f of z1 dot z naught is equal to f of z1 dot f of z naught. So that's the property that you had to prove, and the identity element of R naught is 1. So the kernel of f can be defined as any value z belonging to C naught such that f of z is equal to 1. So it could be so the complex number could have only 1 in its real place, in this real value, or it could have 1 in its imaginary value, or it could have any possible combination such that the mod of the complex number will give us 1. So all those z numbers that whose mod gives us 1, so all those z's belong to the kernel f.